I think Wayne Gretzky would care about what his line means.
Yeah, but I don't think you're
Okay, well, we'll go with it.
Say Mark Messier's game for Gretzky.
Oh, hi everyone. Oh, that's a great way to start our lesson. Yes. Let's take a look today at our new topic, everybody. We are looking at finite differences. This is a classic skill that goes all the way back to grade 9, where in grade 9 and maybe even in grade 10 you were like, why are we doing this? And now it's like, oh, I see why we were doing this. So we will review and we will see how the concept of finite differences allows us to determine the degree and leading coefficient of a polynomial function. And it's pretty cool. It's a really neat property of functions and I hope you'll like it. Okay, so here are the things that you want to check for yourself and make sure that you can do by the end of the lesson is you can calculate and find the finite differences for a given polynomial from a table of values. And you can also see the relationship between these finite differences, between that and the leading coefficient, and the relationship with the degree of the function. So we saw on Friday that leading coefficient and degree really are important for getting a good sketch or understanding what this polynomial is up to as it goes towards infinity and even its behavior around its roots, etc., etc. We're going to also add finite differences today. Let's start with like a little which one doesn't belong. So what do you think? There's 4 different graphs. Which one do you think doesn't belong? Nathan?
The top right one.
Top right, why?
It has an even degree.
The rest are odd degree and that one's even degree. Very good. But we could say that, so this one is the only even degree. That's why we would exclude it. If you wanted to exclude this one, how could you exclude that one? Mateus?
Positive.
Yeah, this one has a positive leading coefficient. And this one has a, what's the coefficient on that one? Negative. Oh, but actually this one is also positive, right? Because it's this dance. So when we're even and we're doing this dance, that means we have a positive leading coefficient. What's the coefficient down here? Positive. Okay, yeah. So we could exclude this one because it's the only one with a negative coefficient. I'll do this one. This one's the only one that has 0, 0 as a root. The rest have, each of them have 2 roots with one exception. But that's the only one with the 0, 0 as a root. Maybe that's the hardest one to eliminate. And this one, yeah, has 3 roots, and the rest have 2. So that's cool. What do we call, so this is a cut root, and this is a bounce root. This one has 2 bounces, and none of them have a drag. Oh, wait, no, none of them have a drag. Okay, how about these? Nah, I kind of want to keep going. Okay, let's, I don't want the lessons to take too long. I want you to have time to practice. All right, and we already did mine's on. So, finite differences. We're going to review this idea. They're the differences found from successive y values in a table of values with evenly spaced x values. We need to be careful. You can't just blindly go start calculating your differences between y. We need to have evenly spaced x values. We don't necessarily need the x values to be spaced out 1 by 1. We could have like -5, 0, 5, 10. And still investigate the differences, but we will find some advantages with x values that are spaced out 1, 2, 3, 4, 5, just by like a jump of 1, okay? Linear functions, we saw in grade 9, have a constant first differences. So if I have a linear function, this shouldn't surprise us that our first differences are constant because we just have the same slope going along and the slope doesn't change as we go. So that creates these constant first differences just from that shape. With a quadratic, on the other hand, you remember the step pattern goes like over 1 up 1, over 1 up 3, over 1 up 5, you know, and the rate at which the quadratic was changing was always changing. So that's why we did not have constant first differences with quadratics, but we do have constant first differences with linear functions. With quadratics, we found we had constant second differences. That's going to connect really nicely for you in calculus next year, where you're thinking that the rate at which a quadratic is changing is constant. Okay, let's keep going. So, oh wait, this is good. Quadratics are second degree. Linears are first degree. What assumptions could we make about higher degree functions and where their differences become constant?
Whatever their exponent is.
Yeah, so if we had a quintic, let's say, an x to the 5, where would you expect to find constant differences? The fifth differences. That would be a lot of analysis that you'd have to do to get there, but you would find constant fifth differences with a quintic. Good. So that's our connection there. So if we have degree n, where n is like, you know, cubic is x to the 3, quartic is x to the 4, etc., where n is a positive integer, the nth differences are constant. Okay? And they will have the same sign as the leading coefficient. That's, again, giving us information about the n behavior, about how we would sketch this function. So it's an important part of our recipe. And the constant differences that you find, the finite differences, will all be equal to an factorial. Hands up, who knows factorial? A few people, only, it was very few hands. Okay, cool. We're going to get to look at factorials today. All right, that's great. One of my favorite little math bits, all right? So we're in an English classroom, but we're going to use the exclamation mark in a new way, where if I have something like 4 factorial, this could describe, like, let's say I have an apple, a banana, a cantaloupe, and a dragon fruit, all right? 4 fruits conveniently located at the front part of the alphabet. I can eat them A, B, C, D, or I could eat them ... D, C, B, A, and I can eat them in a number of different orders. Anyone know how many different orders I can eat those fruits in? How many possible, like, different words could I spell with those 4 letters with no repetition? How would we find that? We just use factorial here. But why? Okay, I have how many choices of fruits that I can eat first? I have 4 different fruits I could eat first, A, B, C, or D. But after I've eaten that fruit, how many fruits do I have left to choose from for my second fruit? 3. In all cases, I've already made one choice here, so I have 3 choices there. And so, and then I have how many choices here? 2. And then after I've chosen to eat 3 fruits, I always have 1 left, and I don't really get to choose that last one. So if I want all the possible orderings, I actually multiply here. 4 factorial is the same thing as saying 4 times 3 times 2 times 1. And these are beautiful little numbers that are really factor rich, and they have a lot of interesting properties, one of which is they're related to our finite differences. We're seeing this math showing up here. When we get that finite difference, we get a times n factorial. Okay, cool. So 4 factorial is how many different ways can I eat the apple, the banana, the cantaloupe, and the dragon fruit? 24 is correct. Yes, 24 is 4 factorial. So a fun way that you used to be able to fool AI was you could say, what's bigger, 120 or 5? And when you said 5 with the exclamation point, actually to a mathematician that means 120 because it's 5 factorial. Yeah. Mr. K told me a great math joke the other day. He said, how many seconds are in 7 weeks? And the answer is 10. Okay. It's a cool thing, the way the factors work out. If you do 10 factorial, that's the number of seconds that are in 6 weeks. Sorry, 6 weeks. 6 weeks. Cool. Okay, anyhow. So how are we going to use this, Mr. Jennings? Let's keep going. And please stop shouting at us. We don't like being shouted at. Okay, fine. I'll try and contain my enthusiasm for factorials. I just want you all to know that I am like doing a thing now for your benefit. Okay, so let's take a look at this example and we'll see how we apply this idea where the constant difference that we find is equal to a times n factorial. Hey, Mr. Jennings, I notice something that I can use to memorize that. What can I use to memorize that? Oh, it's like a can formula. Okay, cool. Let's go. So 45 goes to 16. Is that going to be a positive or negative first difference? Here is a point where you often had an error in grade 9. I don't know if you still make this error, but here is what you want to make sure you do is get the sign right. We do the second one minus the one that came before it, and we're very careful about the sign here. Negative 16 minus minus 45 is the same thing as minus 16 plus 45 is the same thing as 45 minus 16. You just want to make sure you get the number right. This is positive 29, please. Okay? All right, and that's all rough work. Don't please do that in the middle of your analysis. You do that somewhere else on like a cocktail napkin or the back of a receipt. Minus 16 goes to minus 3. I see that gives me 13. I got bigger by 3. I got smaller by 1. I got bigger by 1. I got bigger by 9. I didn't, but the table did. And then this got bigger by 23. Doesn't this look like a mess? Like some kind of weird Mensa test, like find the pattern in those numbers, and you're like, I don't know, I don't see any pattern. It bounces around all over the place. But now, culturally, you're learning this new strategy of we do not have finite first differences. So we're not linear, this function, but we're going to investigate our second differences. 29 went down to 13. That got smaller by 16. We do this carefully. 13 minus 29 is the same thing as 29 minus 13, but the answer is negative. Find your way to get the right answer. 13 goes down to 3, so we are smaller by 10. 3 goes down to minus 1, so we are smaller by 4. 1 goes up to, negative 1 goes up to 1, so we are getting larger by 2. 1 goes up to 9, so we are larger by 8, and 9 goes up to 23, so we are larger by 14. Now we can see the pattern, right? Now you can see what's coming next, eh? You can see what's coming next. You're really excited to do this. Minus 16 goes up to minus 10. We are bigger by 6. We are bigger by 6. We are bigger by 6. We are bigger by 6, and we are bigger by 6. What degree is this function? This is a cubic. Good. This is a degree 3 polynomial. And we just found out that c equals 6. And our n is 3. So we are degree 3. We are constant value 6. So what sign is the leading coefficient? Are we a positive, negative?
Positive.
We're positive here. And so we can tell the end behaviors. We can tell that we are in this situation. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. Cool. And we can even figure out what that leading coefficient is by just using our can formula. So we know can. Write out your formulas first. C equals a times n factorial. Substitute in 6 equals a multiplied by 3 factorial. Work out 3 factorial on your calculator. It's got a button. It's 6. It's 3 times 2 times 1. It's a number of different ways that you can, arrange the letters 1, 2, 3, whatever. The numbers. All right. Okay, and then we keep going. So 6 equals 6a. A equals 1. There's your leading coefficient. It's just that easy. All right. And then you're going to describe your end behavior. And so you're going to do that by saying, as x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, or I should say y here, because this was given to us as y, y goes to negative infinity as well. We are doing this dance. Okay. So let's not do question. I think we're good with that one. So now I'll pause the video. Y'all try this one yourself. You can read that. Yeah, you can read that from the back of the room. That's good. I'll pause the video and we'll pick it up in just a second. We are live, everybody. So, we were here before we took a little break.
Wait, did you unfreeze?
Yeah, I unfroze. Oh, wait, I didn't unfreeze this. There, we are live again. So, did you, who has a finite constant difference that they want to report? What did you find, Eva? Anyone agree? Oh, we have one agreement. Anyone else agree? Okay, because if it looks like this, then you're on the same team as me. Okay, so we have, which differences turned out to be constant here? These are the fourth differences, yeah. And so we have constant fourth differences. So what's our degree? Yeah, it's just 4. It's just that easy. And then our constant fourth differences were minus 24. So I seem to remember there was this really cool can formula, so I'm going to write it out. C equals A n. We're very excited about the n because it's n factorial. And we want to know the leading coefficient and its sign. What's the sign of the leading coefficient? Oh, we got silent again, so let's find out together. All right, so I put these in. C is equal to minus 24. A is, we don't know that yet, and n was 4 factorial. Anyone happen to remember how many different ways I can eat an apple, a banana, a cantaloupe, and a dragon fruit? It was 24. It's right there. So, yeah. So we have minus 24 equals 24a. 4 times 3 times 2 times 1 is 24. So then a equals minus 1. There. And now we could sketch this nice function here. We could sketch it as looking something like this, right? Wait, that might be too many wibbles. Actually, no, that's the right number of wibbles. We have this end behavior. Okay? As x gets very large in either the positive or negative direction, y goes negative. So our blah, 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 what was it? Yeah, so we have an even function with a negative leading coefficient. So we would say as x goes to positive infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to negative infinity. We are this type of behavior here. We are this dance. Okay, so let's keep going. All right, very good, everybody. Now, if we found that the second differences were minus 8, what type of function do we have? Second differences are minus 8. We are quadratic. What is the leading coefficient? It is negative, and do you know its value? Let's find out. Can. C equals an. The c was minus 8. The a is we don't know it yet, and the n was quadratic. N is 2. Okay. Second differences. So we are 2 factorial. Anyone happen to know 2 factorial without a calculator? It's 2, because 2 times 1 is 2. That's like saying, how many different ways can I greet Nathan and Connor? I can say, hi Nathan, hi Connor, or I can say, hi Connor, hi Nathan, and those are the 2 choices. All right, it's only 2. Okay, so there's 2 ways. So this is minus 8 equals 2a, and a is minus 4. There's our leading coefficient, and we know that if we had a quadratic that was minus 4x squared, plus or minus blah, 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 that doesn't matter, okay? We will eventually have this type of shape, right? Or quadratic, it goes down on both ends, it has a maximum. We know a lot already, okay? If we found that the fourth differences were 24, we are quartic. We are n is 4, okay? And we have can. C equals an, exclamation mark. C is 24. We just did this one. a times 4 factorial. 4 factorial is 24. 4 times 3 times 2 times 1. So a equals 1, and our sketch would be something like this. We have this type of end behavior where we're going up on both sides. And again, I'll write it out as x goes to positive infinity, y goes to positive infinity, and as x goes to negative infinity, y goes to positive infinity. We are this dance. Okay, let's keep going. All right, here we're just showing the equations. So these ones should be pretty easy. What constant finite differences would you expect here? They're going to be negative, yeah, because we have a negative leading coefficient. We are degree 4, so we would say can c equals a n factorial. C equals, here all of our unknowns are on that side. Sorry, our unknown is c, so we have all our knowns on this side. A is minus 1, and n is 4. And 4 factorial is c is going to be minus 24. We've already seen this one in table form, but now we're seeing an equation form. More interesting, over here we have a quintic, a degree 5 polynomial. What will its constant differences be? Yeah?
240.
How did you know they would be 240? How did you do that?
So I did 5 factorial times 2.
Yeah, c equals a n factorial. Here, c equals 2 multiplied by 5 factorial. 5 factorial is 120, because you can remember that time I shouted at you, what's bigger, 120 or 5? And yeah, I think now AI will get that joke. So this is 2 times 120. So our constant differences would be 240. Absolutely, very good. Okay, now go practice, everybody. If you need a textbook, I can lease you a textbook for the semester. I do come to classes and interrupt your classes embarrassingly to get the textbook back from you. Oh, but you're grade 12s. I won't be able to do that next semester. So yeah, we just don't give you your diploma until you give your textbooks back or pay for them. If you don't want to take a textbook, I'm just going to pause this video now. I'll talk to you about that. And if you have any questions, people who are watching online, you find me in person, or you email me, or you otherwise connect, and we will look at your things. Thanks so much for showing up for your math learning. Bye.